Welcome back, students. Welcome to the class. Today we will discuss some more reactions of alkyl halide. One of them is neighboring group participation. A number of nucleophilic substitution reactions are known which occurs with an unusual very high rate of the reaction. In these reactions usually there is an atom or a group with an unshared electron pair beta to the leaving group or sometime further away. For example, in this substance, that is the sulfur group is present what? Beta to alpha, this is position is alpha, this is beta to the halogen. That compound is nearly 600 times more reactive than a simple propyl chloride. Why? Because there is a presence of sulfur with a lone pair of electron here. So it means that the lone pair present on this sulfur atom, they are doing or they are participating in a reaction such that it is enhancing the rate of the reaction. Now, the neighboring group participation consists of two consecutive SN2 substitution with inversion of configuration, because with each step of SN2 inversion is involved, and if inversion happens two times it becomes the retention. Okay, so what does happen there? This atom has a more than one lone pair on it, and so it can participate in as a neighboring group reactant. The lone pair will attack the carbon, this carbon, and leaving group will leave the alkyl chain, and a cyclic intermediate is formed. So this is SN2 reaction. So this SN2 is what? It imparts inversion. Now after that, in the next step, nucleophile again attacks. When the nucleophile again attacks there, what happens? That reaction is also SN2. So what you have? You have inversion of configuration happens two times. One in this step, second in this step, and resulting in that the reactant and the product here both will have the same configuration. Why? Because SN2 happens two times. Now first we will look at that when oxygen atom is acting as a neighboring group. Now what is happening here? Now look at that. This oxygen negative charge will attack this carbon bearing the halogen. So this halogen will leave the system and you have a tricyclic state happens here. To this cyclic state, again that is OH negative, that is a nucleophile, it will attack the carbon and ring again opens. So what does happen? You have the retention of configuration here also. Similarly, if oxygen tosyl group is what? This is tosyl group actually. This group is called tosyl group. Okay, so R is this chain, this is R, or you can say that's how it happens to, because every alcohol H is removed from that. So actually this is the compound. Okay, this is tosylate. Now in this reaction, H of the alcohol and Cl of this compound is removed, and you had the formation of that is an excellent leaving group. So oxygen will attack this bond, and this lone pair become a sigma bond here. After that, the nucleophile will attack the same site here, and ring again opens up. So nucleophile join the same position as from the leaving group. Why? Because SN2 happens two times. Because SN happened two times here. Now look at the second case. Now it is sulfur has lone pair, two lone pair, and the position is gamma to the halogen. So what happens that lone pair will attack the carbon bearing the halogen, then halogen will leave the system. After leaving the system, the incoming nucleophile will attack the position, and there is an opening of the cyclic ring, and you had the formation of the product. So here also you will get the retention of the configuration. Why? Because SN happens two times. Similarly here you can have the group nitrogen lone pair will attack this halogen bond, and you have a tricyclic state here. After that OH will attack this carbon because this carbon is less hindered. Why it is not attacking here? Because it is more substituted carbon. So what does happen here? That OH negative will attack this and ring opens up like that, the arrow goes towards the nitrogen, and you have the compound here. So that results also in what? Retention of the confusion by, because SN2 happens two times. Are you getting that or not? Now neighboring group participation by the pi electrons present at the gamma carbon. Okay, this is very interesting example. Now in this case what happens that pi cloud here present at the gamma position, it is alpha beta gamma, you can see there easily, it will attack and forms a cyclic like that. Now after that OH has two sides to attack. Okay, one position is that if OH attack this position, then you will have at this. Okay, sure about that. And if OH attacks this position, then you will getting this compound. So you have two different compounds here due to the, why? Because in the previous case, if you have observed that, okay, this it will attack less hindered. This compound, this is less hindered. Okay, this is less hindered. That's why nucleophile attack the less hindered carbon atom. But in this case, if you can see easily here, both the groups, this contains a methyl group, this contains an ethyl group. So both the groups are equally hindered. Okay, so then what can happen? So OH can attack both the sides. So you will get two products, product 1, product 2. Now look at one more thing, that is SNI, nucleophilic substitution internal. Okay, there are certain nucleophilic substitution reaction which proceed with retention of configuration even though no neighboring group is involved there. Now SOCl2 in ether and SOCl2 in pyridine will give you two entirely different products. Now if you take an alcohol and react with thionyl chloride, the O of the alcohol will attack the sulfur group. Okay, when it attacks a sulfur group, what can happen? You have the first reaction. Okay, clear? Now after that, the ether is present in the system, it will attack the carbon and the reaction follows the SN2. So it means that it is behind, it is attacking, means from the behind side. Okay, not from the front side it will attack. So from the back side it will attack, and you have SN2. So there will be inversion of configuration. Again what happens? Chloride anion is present here, it will again attack this carbon atom from the back side, and you had again SN2, and now you have retention. Why? Because SN2 is happening two times here. Are you sure? Now, if the same thionyl chloride is taken in what? In this step is okay because SOCl2 is taken. Now, after this step, if in place of ether you placed pyridine, then what happens? In place of ether, if you taken pyridine, then what happens? That pyridine will attack this sulfur and chlorine will leave the system. So sulfur and nitrogen or pyridine, they are able to form a bond between them. Okay, after that what happens that now when the pyridine, it will attack the sulfur and chloride ion will leave the system. Then after leaving the system, chloride ion will attack this carbon from backside, and you had the formation of SO2 and pyridine you are getting again, and then now you have inversion of configuration. So remember that thionyl chloride with ether will give you retention, and with pyridine it will give you inversion product, as I told you. Okay, so in ether what happens? Retention of configuration, and in pyridine inversion of configuration happens. Now next reaction is the reaction of the metals. So what is the reaction? The reaction is Wurtz reaction. The reaction is very important. This reaction is a coupling reaction given by halides in which halogen is present on the sp3 hybrid carbon. A reaction takes place in pairs of sodium, zinc, silver, mercury ore and activated copper. For coupling reaction, the two molecular halides are needed. Both may be same or may be different. If both are same and one of them is hydrocarbon with even number of chain is obtained. Okay, so what you have sodium hydroxide taken out and you have formation of this particular reaction is known as Wurtz reaction. Similarly, look at that, this Pr and this sodium, they will pack to give you NaBr. Okay, but if the reaction is carried out between two different alkyl halides, then three products can be possible. One, that R may react with itself to give you RR, R dash may add to itself to give you RR dash, and R and R dash both will them react together. If both halides have even number of carbon atoms or R number, then the product always has even number of carbon atoms. Are you sure about that? If one halide has even number of carbon and other has odd number of carbon, then the products have even number and one product has odd number of carbons. For example, here you have methyl bromide and ethyl bromide. Here methyl bromide has a odd number carbon. So what can happen here? Okay, you will get one of the product, that is propane, as odd number. So this is very, very important. Now Wurtz reaction can undergo two types of mechanism. In the first mechanism, the formation of the product takes place by the formation of an organometallic compound of sodium. This metallic compound has some ionic character and hence carbon bonded to sodium behave as the nucleophile and it gives an SN2 reaction. Remember that tertiary alkyl halide do not give this reaction. So this mechanism is get support from here. So that is very, very important because tertiary alkyl halides, they do not give this type of mechanism, and tertiary alkyl halide do not give Wurtz reaction. That's why this mechanism of SN2 is preferred. But we, in several cases, we are getting side product also. So second mechanism is that the product form take place by the formation of free radical. Okay, then once the free radicals are formed, they can undergo various type of rearrangement to give you disproportionate product. Okay, for example, if you have taken this reactant, okay, then what will you have? You have one butane as the product, then you will have ethene as the product, then you have ethane as the product. So all these possibilities are possible here in this case. So these are some examples of intramolecular Wurtz reaction. Okay, this chlorine and this chlorine, they will give you a cross linkage here. Okay, this carbon will made you with this reaction. This carbon will made you with this reaction. PbCl2 is formed, and these two come, they are fused. This is 1, 2, 3, 4. This is 1, 3, 4. 1 dash, 2 dash, 3 dash, 4 dash. So these are examples of intramolecular redox reaction, intramolecular Wurtz reaction. Now the next reaction is Wurtz-Fittig reaction. This reaction is a coupling reaction which takes place between alkyl and aryl halide in the presence of sodium metal and dry ether. Okay, sure. Now, so you have aryl halide and you have alkyl halide, and then you have products. Okay, so for example, you have iodobenzene and you have ethyl benzene, then you can got one. Okay, so what can you say? That cross product is always the main product in these reactions. Okay, what is Fittig reaction? In this reaction, okay, two molecules of the aryl halide in presence of sodium and dry ether. Dry ether means ether free from moisture. Dry ether, that is very very important, that is free from moisture. What do you mean by that, free from moisture? Free from moisture means that sodium will react with water. So if any water vapors are present there, then sodium will react with the water to give you H2 and NOH. So the purpose of the reaction will not be resolved. Okay. Similarly, alkyl halide will give you coupling reaction in presence of sodium, magnesium, silver, and zinc also. Okay. So coupling of, you have done that in presence of sodium will give you this. Coupling of gem dihalides will give you what? It will provide you alkene. Gem means when the same halogen is present on the same carbon atom. And coupling of gem trihalides will give you alkynes. That is also very important. But in that case, in place of zinc, you will taken silver. Okay, these reactions are called as dehalogenation reaction, means removal of halogens from the substrate. Now you have to understand one more thing, that one of the main reasons of neighboring group participation is that the intramolecular processes has been taken place, and that internal process has more favorable entropy than do the intermolecular processes have, because the two supporting groups are not required to come close together. Okay, 5 or 6 element ring are formed with reactions rate that are typically 10 power 6 times faster than the acyclic reactions. So you can say that the reaction within the molecules are 8 power 6 times faster than that of acyclic. Even a 3-membered ring forms about 10 power 3 times faster than a similar acyclic process. Formation of 3-membered ring is due to more promiscuity effect than the entropy. For example, the formation of an epoxide from the chlorohydrin requires only a small movement of atoms for bond formation. The oxygen anion is about 250 picometer away from the carbon bearing the chlorine. Okay, so it means it is very nearby, and what you have, okay, since it is only 250 picometer, okay, and the bond length is 150 picometer, so that is within the reach. That's why it can act as the neighboring group participation. Now this is resonance description of the chlorobenzene. Now here you can see that at ortho position the minus charge is on carbon. Now in this case at para position there is a negative charge on carbon, and again at ortho position there is a negative charge on the carbon. So this, what is happening here, lone pair becoming pi bond and pi bond becoming lone pair, and that's how the resonance goes on. Now here what happens that due to this particular resonance, that due to resonance, what happened, due to resonance carbon halogen bond acquires a double bond character. So a double bond character has been acquired by the carbon halogen bond. So this will make CX bond or carbon halogen bond shorter and stronger. Third, carbon is now sp2 hybridized, so it means what, it get higher electronegativity than sp3 carbon. Sure about that or not? Fourth, the nucleophile experience repulsion from pi electrons of the CX bond. That is also true. Sure about that or not? And the fifth one is that phenyl carbocation, if can form, phenyl carbocation is unstable. So these 5 particular points will indicate that chlorobenzene does not undergo nucleophilic substitution. Okay, so what can we say, that chlorobenzene, like any other vinyl halide, does not undergo nucleophilic substitution reaction, but if benzene ring also carries some electron withdrawing groups, if benzene ring also carry some electron withdrawing groups, then carbon halogen bond can undergo cleavage. the desired product. For example, if you taken chlorobenzene and react with a nucleophile, nothing will happen. But if in place of chlorozine, if you put more one group nitro at either ortho at revolution, this will weaken the carbon halogen bond and the attacking nucleophile can easily displace chlorine. So one can easily say that presence of electron withdrawing group promotes the nucleophilic substitution in benign halides. Now if you react a nucleophile with order K1 and nucleophile with rate constant K2 and nucleophile rate constant K3, then what you have observed that in each and every case you had the replacement of halogen by nucleophile. But in this case, what happens? Now, if you look at that here, this has 3. So K2 will be greater than K3, greater than K1. Why? More the number of electron withdrawing group, more will be the rate of the reaction.